Hello everyone, welcome to my videos on elementary differential equations. This is video number 23 for chapter 3, and I plan this to be the last video for this chapter. In this video, we continue our study of applications. We will look at the Springmass model, and in this video, we consider the case that an external force is being applied to the model. Therefore, we consider an equation of this form: mu double prime plus gamma u prime plus ku equals F, where F is an external force which is non-zero. Okay, and m is the mass, mu is the damping constant, and k is the spring constant. And for the discussion of this chapter, we will restrict the external force to the following form. F as a function of t is F naught times cosine Wt. Okay, F naught is a constant and W is a constant, so it's a cosine function on the right hand side basically. So we put a remark here: the case where you have a sine function is totally similar, and we'll skip it. And if you're interested, you can go through it after you have learned how to deal with cosine, and go through it, put a sine in, and see that it comes out with totally similar results. Now, just a comment on why we choose this particular choice of the external force to be a periodic oscillating perfect oscillation function cosine. The reason is for later use. We'll see that later. We'll learn a thing called the Fourier series, which is a series consisting of sine and cosine function, and we will use these series to represent periodic functions. And for linear problems, there's the superposition, the principle of superposition. So you can treat each term separately. Therefore, studying a single cosine term or sine term on the right-hand side is very meaningful. Okay, so later on we'll come back to this. Okay, so two cases we want to study. One is the system has damping, so the damping gamma is non-zero, so strictly bigger than zero, for this equation here, where the right-hand side is a cosine Wt. So this is a linear equation with non-homogeneous right-hand side. So we know the solution consists of two parts. The first part is the general solution to the homogeneous equation with 0 on the right-hand side. And the second, capital Ut, is a particular solution for the non-homogeneous equation. All these we have already learned. And now, from the discussion in the previous video, the previous subchapter, we know that the solution for the homogeneous equation will go to 0 as time goes to infinity if the damping term is present. Okay, therefore this part eventually goes down to 0. So we call this part of the solution the transient solution, because it exists for a short time, then it becomes very small and insignificant. Now, the appearance of the particular solution, capital U here, is due to the fact that we add a non-zero force term, F. Therefore, this term is also called the forced response. It's the response to the force term you apply to the spring system. Okay, so we know that the form of this particular solution, because F is a cosine function, therefore the particular solution will have the similar form, which is a sine and cosine function linear combination. So capital Ut would be cosine Wt times A1 plus a sine Wt times A2. for some constant a1 and a2. So as we have seen previously, we know that a solution like this can be written as a cosine function with an amplitude r and with a phase shift delta. Okay? And we also see that this is now in this form, it's a periodic oscillation and has the same frequency, the oscillation, the same frequency as the fourth term. And we see that as time grows, the UH, the transient response, will go to 0, and therefore the solution will asymptotically approach the particular solution, capital UT. Okay, so exactly for that reason, this solution, capital UT, is also called the steady state, the long-term solution. Okay, let's look at the second case, case 2, that is without damping, where gamma equals 0. And this is actually a more interesting case, even though it lacks one term. So the equation now is mu m times u double prime plus ku equal the fourth term, f naught cosine wt. Now we know the solution for the homogeneous equation is also a sine cosine function, right? So, and the frequency of this, let's call it W naught, is square root k over m. So we just call this W naught now, and this frequency is this system naturally would have, so we call this the system frequency. And that is the frequency for the free oscillation without the fourth term here. Okay, so for this problem, then the solution for the homogeneous equation can be written as a linear combination of cosine and sine of W naught t. So cosine W naught t, sine W naught t, and C1 and C2 are two arbitrary constants. Now we need to find the form of the particular solution. Now we see that the particular solution form would depend on the value of this frequency W. We'll have two cases. One is when this W does not match the W naught of the system frequency, and the other case is when they match, when W equal to W naught. Okay, let's consider the first case when W does not equal to W naught. Then the particular solution can take the same form as the right-hand side. So we see that U equals A times cosine WT for some A to be determined. Okay, so I want to put as a comment, a remark to say that we did not put in the sine WT term in the particular solution. In general, for a general and second order equation, we would put in there. But for this one, we don't do that because the left-hand side, in the equation, there is no u prime term. You have term u and you have the term u double prime. And if you differentiate this twice, you get cosine back. So the sine term will not be present. Okay, let's find the constant capital A. So u double prime will be negative w squared times A times cosine wt. So we can plug this in the equation. So this is m times u double prime plus k times u equals f. Okay, and if we drop the cosine term here, we see that we have k minus m w squared times A equal to f naught. Okay, we see that then we have this simple equation and we can solve for A. A would be just f naught over k minus m w squared. So now I would like to manipulate a little bit and write it in a different form. It will let us explain interesting phenomena. Now let's take out the term m, move it outside, and then we'll have a k over m here minus w squared. And remember, what is k over m? Square root of k over m is w naught. So this term is w naught squared. Okay, so a can be written as that. Now, from this expression, it is easy to see the following observation. If now w naught and w are close in value, then the denominator here is close to 0. Then the a would take a large value. Okay, and then we can write out the general solution, which is this is the solution for the homogeneous equation, and then this is the particular solution. And you see that this solution consists of just sine and cosine functions. These two functions, the sine and cosine, has the same frequency w naught, but this term, capital A cosine, has a different frequency w. Now let's consider an example for a special initial condition. So assume the initial condition is u at 0 equals 0 and u prime at 0 equals 0. What does it mean? Well, that means initially your system is at equilibrium and not moving. And then force is being applied to the spring and the system will start to move purely as a response to the force term. Okay, we can find the C1, C2 value in the solution. So u0 equals 0 and you plug in 0, then you get C1 times, that's the cosine term, which is 1, and the sine term is 0, and then plus a equals 0. So C1 is negative a. And then u prime 0 equal to 0, and that will give you 0 plus w naught C2 equals 0, which lead to C2 to be 0. Okay, a little bit detail here, but you can simply work it out. Okay, so then this gives us that solution has two terms only because C2 is now 0. So I get negative a, which is C1, cosine w naught t plus a times cosine wt. And we can take the a out, and then it's just a cosine minus a cosine, but with two different frequency. Okay, so we have the sum of two cosine functions with frequency w and w naught. And what do you think a function like that would look like? Well, in order to see the behavior of such a solution, we can apply some manipulation using one of our favorite, my favorite, maybe yours also, trig identity. So cosine of a minus cosine of b is 2 times sine of b minus a half and sine of a plus b half. Okay, if we use that, and then we see wt is angle A, w naught t is angle B. By this relation, we'll have ut is 2a times sine w naught minus w naught over 2t and sine w naught plus w over 2t. So I write as the sum of two trig function terms into the product of two sine terms here. And now how does this function behave? Let's make some observations. So first we see that w naught w are frequencies, so they're both positive. then the term, if you add them up, will have bigger absolute value than the term where you subtract them. Okay, so then we see that this term here is an oscillation that oscillates faster than this term, which is an oscillation with a slower frequency. So in this case, you can view this function as a function that describes an oscillation with varying amplitude. So you can basically say this is the oscillation, that's the frequency. It's oscillating and its amplitude is changing following this function here. Okay, so one situation here is of particular interest. Is the case that W0 doesn't equal W, but they are very close in value. Okay, and then we would have the difference between them will be rather small and much smaller than the sum of these two. Okay, and then we can show an example to see how the function looks like with a particular choice of W naught and W. We chose it to be W naught is 9, W is 10, and we plotted it function out where A is 1, and it looks like this. So what does it say? You see that the oscillation is the one with 9 plus 10. That's this term here. That's the frequency of your oscillation. You are oscillating with this frequency, and then at the same time your amplitude also changes, but with a much slower frequency, which is 10 minus 9 with 1 and actually half here. So you see you see an oscillation with amplitude varying. So if this shall be an wave, an acoustic wave that you can hear, then you will actually hear a beat, boom, boom, boom. So this phenomenon is called a beat, and we also call this solution a beat. Okay, here's the second case, 2b, where W equals to W naught. Then we know we can't take the same form of the particular solution because it matches the homogeneous solution, and therefore we need to take it and multiply by an additional t. So how does the solution look like? Well, you know that this is an oscillation with certain amplitude and phase. Therefore, you can think it's an oscillation, and the amplitude is growing linearly in time. So typically the oscillation, if initially will be 0, will look like this. So you can see that there is a line t and a negative t, like the envelope, and your oscillation is in between. It has the same frequency as the system frequency, but the amplitude grows bigger and bigger. Okay, so this phenomenon is called resonance. And it happens if the frequency of the force, the source term W, equal to the frequency of the system W naught. So in this case, even a small source term could make the solution grow very large if you wait long enough. Okay, so let's do a summary of forced vibration, the whole summary. So first is with damping. If you have damping, then the UH homogeneous solution is called the transient solution, and then plus the forced response term UT, which is called the steady state. And then if one does not have damping, gamma equals 0, then there are two cases. And if W equal to W naught, then we have resonance. If W doesn't equal to W naught, then you have a solution of is cosine minus cosine. But in the case where they are very close to each other in value, then you get the beat as your solution. Okay, so that is all I want to say for the forced vibration. We will not go through concrete examples. They will just give you the same solution form, but with specific numbers for the constant term we have presented here. Okay, so we just talk qualitatively how the solution would behave in these cases. Okay, I hope you enjoyed this video, and next time we'll start a new topic, and I look forward to seeing you there. Bye bye.